Welcome everyone to the last part of the Acreon tutorial series from dynamics to uncertainty, where we are now going to take into account uncertainty in the plant. And in this case, I'm taking the pendulum, the mass of the pendulum to be varied by 15%. And then using a polytopic LMI, specifically the H2 representation that we covered before, and stepping through that, followed by doing the shadow pricing so we can analyze the solver result relative to our controller and observer synthesis, and then at the end analyzing from Python control a step response, a four step response, and then a Gymnasium rollout with basically the discretized dynamic compensator in the loop with the disturbance that's applied to the cart, and then in addition to varying the mass. So we'll have two different rollouts for a lighter pendulum mass and a slightly heavier pendulum mass. All right, so let's begin. So in this part here, as I just mentioned, the H2 representation, we're gonna now do it as model it as a polytopic LMI, and essentially it's fairly straightforward. We use the same representation from the H2 synthesis, and we're using the same decision variables. However, now they just need to be solved over a polytope, and this polytope is basically parameterized by a interval set between 0.85 of the mass of the pendulum to 1.15 of the mass of the pendulum. And this is just a simple convex combination of the lighter plant and the heavier plant with respect to the pendulum mass. The same representation could be done for the mass of the cart as well. I did that offline too, and I can talk to that at the end with some interesting results. But essentially at the end, what we are solving for here is a intersection of the LMI feasibility space, and that's all convex. The decision variable space is the same as aforementioned. It's just an additional constraint essentially. But then we essentially kind of get into this more robust modeling. So this, I'm not stepping into like mu synthesis or anything like that, but this is kind of on the way of that path. However, polytopic LMIs is kind of a nice, I think it's a little bit more interpretable too, because you can vary whatever your your parameters of your LTI system, and then basically cast that into a convex problem and then solve. So you get a joint. So you basically get a robust controller and observer for the modeled polytope. Now I'm not saying robust stability or performance quite yet. I think I'm going to do that for a different tutorial series, but it's kind of on that trajectory that we can see this. So here I'm varying the mass of the pendulum by 15%. This is just a simple function that varies the Cartpole A mass of the pendulum by this varied amount. And then this is just vertices that's stacked together. And then, because we're like I said, we're gonna have basically a set now of the plant, and we need to now synthesize. Well, it's going to be casted as a set intersection for the LMI feasibility space now, and it's going to be more of these A, B, C, D's right here. So we're repeating these vertices, so we get this kind of tensor structure here that just is essentially the amount of plants that we are now putting into this control synthesis problem. So this is the polytopic state feedback solver routine here. Note that the dual feasibility tolerance is bumped up a little bit here, and in the shadow pricing you'll see much more clearly where this is coming from, and it is more of an optimization artifact relative to the problem that we are posing. And I'll step through that, but it is interesting. I think the 1E minus 3 and that tolerance level, we get good certificates relative to the Lyapunov stability. Once we bump it into 1E minus 2 um, land, that's where things I think get a little bit more quasi stable because we start hitting more degeneracy cases, and I guess I'm just already starting to talk about it. But when I essentially use the mass of the card, it's much heavier than the mass of the pendulum. So then say we vary that by 20%. This guy gets, bumped up a little bit more because the solver, we can get like a primal certificate or a primal dual, but we can't solve complementarity, primal, and dual all at once nicely. So if we bump up the tolerances, we can get an optimal satisfying Lyapunov certificate. However, if you do the pole plots, a lot of these are stacked right next to the origin. So we're really coming up close to really this kind of not so stable regime for stability. And so when when we roll out the Gymnasium, you can really see like how it's handling, but it can get basically whacked into a mode that's unstable. For this scenario here, that's not the case. We can actually pump up this uncertainty of the mass of the pendulum even more if we want, and then relax these terms a little bit better. The mass of the pendulum is significantly lighter than the cart. And then likewise, the dominant pole that we walk through in this notebook is associated more with the pendulum control, right? It's much more controllable than the cart. So I kind of just alluded to that, but we're using the pendulum, so apologies for that tangent, but it was just worthwhile calling out because if you were to play around with this a little bit more, you can kind of see that. So we get the state feedback here, so we get our controller for the H2 polytopic LMI here, and then for the observer below, same thing for the Leuenberger observer, and then I'm getting the poles here, and then I'm going to plot them. So let's see what it looks like. All right, so we can see, interestingly, that we start getting kind of more of this like stacked pole coupling, which obviously, like, it's fine. It's on the left-hand plane, but the one thing obviously is with the transients, and I think what I was alluding to with the cart, if I were to vary that and then bump up the uncertainty, that's where we can kind of hit a little bit more of this kind of quasi-stable cases. These poles here get closer to the origin because it seemed like these are more with that, slowish mode with the cart versus here's the pendulum up here. Anyways, just a kind of a thing that I noticed. And then the polytopic observer here, so we kind of get these sort of stacked representation as well. And then for the compensator, it's assuming the same exact form that I walked through before. And so I'm, tying together the controller for the polytopic and the Leuenberger observer for the polytopic, so we get this dynamic polytopic compensator now that has consideration for the varying pendulum mass. And so I'm getting the poles. This is just the discretizing the compensator that I guess I've been kind of lax about it, but I've been printing it off just so for posterity. And then I'm also going to do the exact same thing here with the full plant and the loop with the compensator so we can see the full pole representation. So this is the poles of the compensator, and then here's the full plant with the compensator and the loop. So we can see much more poles. Kind of has this interesting little arrow, and that's kind of represented with the more of that observer shape here as we kind of vary. And then the state feedback kind of, has more of the poles right on the imaginary axis and then a little bit outside on the imaginary plane. So a little bit more oscillatory behavior on the observer, a little bit less on the controller. With the full, dynamic compensator here, we kind of have this, pole plot, which is, interesting. So now we're going to jump into, so again, I was talking about this a little bit, but we've synthesized the state feedback, state observer, The LQR and LQE, that was done by the continuous time Riccati equations. So those were not running with my semi-definite programming or conic programming solver. So that's not shown here. But we have the H2 feedback and observer, and then we have the polytopic H2 feedback and observer that I just stepped through. And so I've been kind of playing around with this summary. Right now, the cone variables, I have it so you can essentially trace through from the convex constraints all the way to the individual cones that get represented in the actual conic programming that goes on, which gives really nice feedback. The one thing I don't have, which I really would like to have, I think in the future, is to have it serialized such that the auxiliary variables, i.e. what's lifted, like we showed that epigraph lift before, that was manually done. What actually happens with DCP, or the discipline convex programming, we start bumping up lifting spaces for these inverse perspective kind of way, right? So we have these kind of epigraph or hypergraph, depending on if it's convex, concave representations. And so when you go to the cone like the individual cone that gets solved jointly, you can see how like tight it is, like it being the solver routine and the primal dual sense, how tight it is with the margin with respect to each cone. However, the cone variables that I get back at this moment are flat in space, so I don't have insight right now into the auxiliary variables, unfortunately. So this is more of a just basically like norm representation here for getting that dual pressure by cone, pressure versus the residual burden with respect to the primal residuals. The cone health diagnostics will show a nice heat map similar to that Gramian that I showed earlier, with the log scale primal dual norms, and then the complementarity. This is raw, so again, another parameter that emanates, or with the primal dual conic programming, there's a barrier essentially that gets encoded. So I don't have that, but it's raw complementarity, so you can actually, if you were to normalize it by the barrier, it would actually be a little bit lower, most likely. The primal residual burden is at the end, which was shown above here, kind of tracing through. The last plot here is kind of an interesting scale balance between the primal and the dual scale. Again, these are all just like norm based off of the conic variables that get passed back, and it's log scaled. So we shall see it. All right, so this is the first one, the dual pressure by cone block. And so pretty interesting in my opinion, because you can essentially see all of this, I'm going to say loosely, economic utility here, because we're working in the Lagrangian dual space, the dual cone variable here. The direct observers and state feedbacks, when they were basically minimizing a zero optimization function or just feasibility, we're chewing up all of that utility. We're getting really nice tight boundary with the solver, so it's easy to solve. That was kind of shown above, where the time to solve was very quick. So there really is no dual pressure. The primal side, we were able to basically get tight, and yeah, so like that's pretty straightforward. Now, more interestingly, when we get up to the H2 state feedback and observer, that's where we get more of that pressure, so to speak, where there's more of this economic utility left on the table. And that's really because of the amount of constraints that we're starting to impose on the solver. So there's the polytopic and the state feedback, and I just said they're relatively similar to one another, and that's because the decision variable space is the same. So you can see 45 here, that's the amount of variables with respect to this, this cone 0, that's a positive semi-definite cone. You could trace through here, going all the way down. We have some second order cones too down here. So yeah, I think right here I color coded them, so these are second order cones that you can see here. So the so the state feedback, we have, more variables that we're optimizing over, and basically we're running up against a wall in the primal space where the residual burden, if we map it over to here, we kind of hit a little bit of this kind of tolerance here, -4. Again, this is sort of this EPS plus residual norm here, and then it's on the other side is that dual pressure proxy, so this exact same thing here. So they kind of all basically are riding this residual boundary. And then, so the polytopic is basically very similar here, and then the observers are a little bit lower, and probably because of the amount of variables that we're dealing with. And also, we have to understand that primal dual solvers are doing it, the full, convex program gets cast into these cones, and it's solving over joint cones, essentially, this kind of conic space. So it seems like the observers are able to have a little less dual pressure than the state feedback ones. And then this is basically just showing that as a scatter plot between the two, so the dual pressure and the residual burden, as mentioned, kind of riding this -4 boundary here. Again, log scaled. So, and then the cone health is interesting. So again, this is basically primal dual scale, complementarity, and residual. And this is kind of a nice little graphic because it shows that the residual, again, -4, it's pretty good that we're chewing up that primal residual space, meaning that the problem is well posed. And then the complementarity is hung a little bit, and that's just because the primal and dual scalar are a little bit higher. So the dual is really what's the burden that we have for more of these complex synthesis problems, whereas the primal is a little bit more, we're able to chew down that space, so with respect to the solving routine that goes on. So then, and then here you can see really, with the direct state feedback and state observers, the residuals are really completely chewed up to close to 0. Dual scaled. This is kind of the nice, we have a little bit more primal, but we've chewed up all of our relative economic utility where we're getting nice optimal solutions. So you can kind of see, right? If we were to relax some of these constraints, we get down to here, which makes sense because these are the most lax, relatively speaking, for the state synthesis and state observer synthesis problems. And then for the primal dual scale balance, so this is interesting. Again, maps pretty cleanly here to that primal dual scale here, so we can see exactly that the for the direct state synthesis and observers, these dominate, right? The primal scales dominate, versus on the other hand, with the more complex control synthesis, the dual starts dominating. So we have more of this, again, utility that's left on the table, so to speak. And the complementarity is just like higher because of that when we take that inner product and normalize it. So I think it's pretty interesting. It gives more of an insight to what's going on in my solver, tracing all the way through to the constraints, so to the cone program, and then it gives you a little bit more information on when you synthesize the controller K and L, what is actually going on. So all right, now this is the final piece. So simulating and gathering some of these results. So the dynamic compensator is operating on the measurement x and theta that gets produced, and then we produce a force command U. And so we also have that disturbance channel W that goes through the same physical force channel U as mentioned above. And then the rollouts here, I mentioned it was kind of like this bang-bang, not purely bang-bang control. It's quantized, where the Gymnasium essentially just has these discrete commands, like 1 and 0 for left and right. And so they kind of, yeah, act like these larger impulses. Oh wait, no, sorry, this was just plus not 10 plus 10 minus 10 10 newtons quantization. Stabilizing commands behave like large impulses. So I have a clipping that goes on in the rollout itself that I'll show below. So the simulations, we have the 4-step response that is like the, MATLAB, but I'm using Python control, so it's basically just simulating a 4-step response on the W channel is 1 Newton. And then the state trajectories for the Gymnasium rollout with an artificial pulse. So I just do a square wave pulse for a certain time duration after the system settles, and then the same rollout while varying the pendulum mass. So then there's 2 more rollouts where we have a lighter pendulum and a heavier pendulum. So this part right here is just the compensator specs for each one. So we have the LQG H2 and polytopic H2. This is setting up the plant plus compensator system that we've walked through before just doing pole plots. And these are getting the dimensions quite right. Again, enumerated above with the law tech in the markdown. This was the force pulse here that I was talking about. So basically, time is greater than or equal to 0.35. It's tunable, and the time's less than 0.75. Apply this, basically square pulse on the disturbance channel. It's set to 0.75 newtons at the moment. Simulating the system, so that's a closed loop system. Time that gets put in to the force response, and then U is disturbance. And then you can see here, this is just compute the output of the linear system given an input. So yeah, pretty straightforward. I get the Y output, transpose to get it more, I think it's row Y, or yeah, it's a row vector by default, so this is just putting in the column. And then the discretize the controller. I've done this sporadically above, so this is just a utility that takes the nominal controller in continuous time and then performs a nominal 0-order hold right now on it, and discretizing it by the DT from the that's from Gymnasium. So we get this controller D, and I think it's like 0.02 seconds or something like that. So then we get this discretized ABCD from the controller, our dynamic controller that is, here. This configure pendulum mass, so this is taking the environment from Gymnasium and the varied mass that I'll show below. And then this is just setting it, so from the model we're resetting the mass pull, total mass, and this is kind of a weird, I guess, I don't know, unit that they want is this pole mass length, so it's units kg by m, I think. Anyways, so setting these parameters before that rollout for when we vary the mass. Here's the rollout itself. So it takes in the controller, and then these are the keyword arguments below for the initial state, pendulum mass, disturbance, steps, seed, max force, and then right now I have capture frames off. If you want capture frames on, you need to, what is it? There's like another like Python module that you install. It's not it's like an adjacent to Gymnasium, but anyways, you can plot out the rollouts if you want, so you can see the pendulum stabilizing. So yeah, here essentially we're getting the simulation set up. Configuring the pendulum mass for whatever's input, that's just resetting the environment, getting the state, discretizing the controller, and then this is more state initialization. Here's the actual stepping of the simulation routine itself. So get the state, and then we project that to get the measurement from our C matrix, right? So we're sensing the cart position and the pendulum angle. And then with our dynamic controller, if you remember so this is getting the U output, right? So this is basically, because we're outputting a U is our force command. So the feed through is our that compensator operating on the measurement, and then we have the control state the C operating on the control state, and that's again in our dynamic compensator frame, not just like C, like a vanilla C. It's we packed it into a nice dynamic controller compensator, sorry, and so that's what that C and D is at this moment. So that's our force command here, and then if we if we have disturbance coming in, this is where the disturbance. So there's a I guess in C++ land a functor kind of thing. So or a lambda utility here that takes in the step in the cartpole that gives us the time at this duration or at this time step here, and so then this tells us if we apply that square wave or not, or that pulse rather. So then the applied force here, I'm mutating the force command and the disturbance force, and then that's normalizing between minus 10 and 10. So that's absolute value here, and then so this is the action. So this is the discretization, or sorry, quantization rather, of the applied force here, whether we go right or left. Capture frames append. This is just appending the states, appending the controls for visualization later. And then this is stepping the environment with the action. We get if it's terminated or truncated, and then we get the next controller state here. Cool. Close up the environment or the simulation, and then we return states, controls, frames. So that's a bunch of boilerplate. So the first one here is the 4-step response plot. So this is just basically a persistent unit step, 1 Newton on the disturbance channel, and it's the plant state response for with the dynamic compensator in the loop. So it's more operating as a disturbance rejection rather than a reference tracking thing at the moment. So it's pretty interesting. We can see that the H2 and the polytopic H2 are obviously much less sensitive to that disturbance being active, whereas the LQG has much more amplitude for that that step response here, right? Takes a little bit longer to settle, and we're obviously controlling the theta, so it doesn't really matter about the x. It does take a little bit longer of an arc for H2 and polytopic H2, but it is also interesting that it settles around this like minus 5 meter position versus this kind of swings out and swoops back kind of thing. So it takes like a longer, trajectory, so to speak, to stabilize the pendulum, whereas H2 and polytopic H2 does like a smoother stabilization and settles at that minus 5 meters. And here are the rates. So again, LQG much bigger arc amplitude here, big oscillation, whereas the H2, polytopic H2, much less. So that's the first one. The second one here, linear state trajectory plot. So this is applying that rectangular force pulse. So a little bit different. So wait for the system to settle, and then we apply this pulse, and then remove it, and then see how the settling works. So again, we can see it. So we get this, again, similar oscillatory behavior for the LQG that's much more pronounced than the H2 and polytopic H2. I would say, again, much smoother trajectory of the cart. Rates follow that as well. The theta dot 2, it has a more of a lagged response to on the LQG versus the H2 and the polytopic H2. So far the H2, polytopic H2 are mirroring each other fairly similarly. The LQG is stabilizing. It's just perhaps not as smooth, and that could just be with Q and R, tuning as well. So, but we are also using the same Q in our Cholesky factors as well. So just to note that, and we're getting that Lyapunov certificate and a lot of other things too, right? So it's encoding a little bit more of that disturbance rejection with respect to that W channel. So here we go. So this is Gymnasium rollout now with the disturbance channel active. And so this is where things get interesting. So we can see now that LQG is terminating, right? So it is getting unstable and terminating after that pulse is applied. And I think this is really where we're starting to see that difference between a more robust control mindset and a optimal control, where we no longer have these guarantees and starting to really show in the LQG versus the H2 and polytopic H2, because we can, I mean, the LQG terminates, it's becoming more unstable, it can't stabilize the pendulum, that's going, uncontrollable, whereas the H2 and polytopic H2 are able to stabilize. And, a large factor here is because of the quantization effect too. So the H2 and polytopic H2 are, handling more of these nonlinearities in a more uncertain mindset, whereas the LQG has more of this optimal control mindset, and it doesn't factor in the disturbance, the uncertainty, and the Lyapunov stability criterion of that synthesis. And we walked through both of those cases, and so it's much more apparent here. Whacking the system, we have more of a discrete simulation. We have a quantization on the actual control itself, and it becomes more unstable. I think this is we are simulating it, so it's obviously in Gymnasium's by no means a Sim2 real platform, but you can only imagine with say a quad rotor or something like that, you have a mixer between the rotors or the motors that control the rotors, and all of that's nonlinear. So when you apply this command here for stabilization effects, you're not really modeling any of that. That's still down the pipe of the control. And so when you want to have more of that uncertainty and robust mindset here, mixed with the optimal, right? We have minimum energy control here with disturbance rejection. This gives you that clean framework. And again, peace of mind here, where we see these nice step responses. LQG is still okay on that, just unit step, and then a step with that square pulse or the force pulse. But then really when we start simulating it and adding more nonlinearities, more uncertainty, LQG is starting to struggle, H2, polytopic H2, working fine. So the last bit here is varying that mass of the pendulum, and we roll it out with the 2, or I think it's just 2 at this moment, but basically minus 15% of the mass of the pendulum, plus 15% of the mass of the pendulum. And we can see LQG struggles even more. It terminates even earlier after we hit it with a impulse, that force pulse. Interesting thing here, and I think this is what I was talking about it before with the mass of the cart. We're using the pendulum right now. It's much more easy to control. It's much lighter than the cart. So H2 and the polytopic H2 are actually pretty compatible. They're relatively, clean. You could see maybe a little bit more behavior that's perhaps a little ideal for polytopic H2 settling, perhaps, less movement, but H2 here is a little bit more of a damped response, so they're fairly even with this varying the mass of the pendulum. When I vary the mass of the cart, you get a different story, especially when you want to vary it even more extreme. You just run up against those slower modes that start getting more degenerate as the synthesis, the solver is trying to basically solve that intersection of LMI feasibility that's becoming increasingly more difficult with a very heavy and a very light cart. But then you can see that the H2 will drop off, and then the polytopic will continue on. However, again, as aforementioned, you kind of need to play around with it a little bit, because once you get these poles closer to the origin, obviously it's not ideal. You want to have, the poles further out, so you have faster decay responses and better LMI or better Lyapunov certificates. Once you kind of relax some of those tolerances that the solver is giving you, you're kind of snaking around it a little bit. You're getting a Lyapunov certificate, but you're also getting poles that are closer to the origin. Anyways, it's kind of some food for thought. It is interesting on the whole. And I think it's, pretty cool to see that, okay, we get nice, robust, optimal controllers with H2, both polytopic and H2, and we're able to solve efficiently, and we get nice responses on the Gymnasium rollouts with the disturbance, with the mass variation, and this definitely shows you where things kind of lie in terms of like optimal control and then getting more towards the robust control. And so again, I appreciate everybody tuning into this. I think this was pretty enjoyable for me. If there's anything that I can improve on, I'd be glad to hear it and to apply it to the next tutorial series, if you will. One of the quotes that I like is a Feynman quote where he essentially states, and this isn't verbatim, but essentially you can't create what you don't know. And so these deep dives are pretty nice because I think you get a little bit of a piece of the pie, not the full slice, or vertical, if you will. So it is nice stepping through things very rigorously and then really understanding what's going on at an end-to-end level. So thanks again for tuning in, and I hope you all have a good rest of your day. Thanks.